my dear friends, the wave-particle duality is a postulations that all particles exhibit both the wave and particle properties. It is a central concept of the quantum mechanics. From a classical physics point of view, particles and waves are distinct concepts. A particle doesn't exhibit the wave-like properties, and a wave does not exhibit particle-like properties. However, our scholars, they accepted the wave-particle duality after several groundbreaking experiments. In the earlier of the 19th century, the double-slit experiment by the scientist Thomas Young, provided the evidence that light is a wave. Then in 1861, scientist Maxwell explained light as the propagation of electromagnetic waves. Now in 1924, Broglie, a French physicist, formulated the Broglie hypothesis, claiming that all the matter, not just the light, has a wave-like nature. His hypothesis was soon confirmed with the observation that electrons also display diffraction patterns, which is diffraction is a property of a wave. And electron, they are exhibiting the same diffraction pattern, what it implies. So therefore, that's the reason that de Broglie theory can be extended to show that all matter exhibit the same wave-particle duality as the light. This means that everything in the universe can act like a wave. But you may not be agree with me. Why so? Like, why do we not notice a football in motion acting like a wave? Well, in the classical mechanics, the particle travel along well-defined trajectories, moving in the three-dimensional space as the time progresses. Right? If we throw a ball, it travels along a parabolic trajectory until it hits the ground. If we know the starting position and velocity of the ball when it was thrown, then we can figure out exactly which trajectory the ball will follow and exactly where it might be at any time after it is, thrown. So we can even calculate the exact location of the ball, and may eventually the land. And there is no uncertainty. But no, in case of the quantum mechanics, the particles do not move through the space along well-defined trajectories. If we launch an electron, for instance, we only know the probability that the electron is at a particular location and at a particular time. So we can only state the probability that the electron will land at a particular location. In the classical situation, our initial conditions were both exactly precise. We know the position and velocity of the ball precisely at the start of its motion. In the quantum case, our knowledge of the electron's initial position and momentums are not precise. The more we know about the starting position of the electron, the less we know about the starting momentum, and vice versa, as this is the uncertainty principle. Therefore, it is impossible to precisely specify the electron's initial condition at launch. The most we can specify is the only probability that the electron starts out in one region of space, and similarly for the momentum. Okay, it is just the probability. This was the quantum mechanics. Photon of frequency, frequency nu, and which is having a momentum p. P is equals to h nu by c, simple relation. Now c equals to nu lambda. C is velocity of light. The relation becomes simply lambda is equals to h upon p. So very important relation. Lambda is the wavelength of a photon, a wavelength associated with a photon, and lambda is equals to h upon the p, where p is the momentum. And the momentum of a photon is h nu divided by c. Now this is the relation for the photon. Now the de Broglie waves, lambda is equals to h over p for the photon, and de Broglie suggested that the above equation is a completely general equation. General means applicable for the matter also. Lambda is equals to h over p. That can be applied to the material particles as well. Okay, and as well as to the photon. But the momentum of a particle will be mass m and velocity v, and that momentum will be gamma mv. Why it is gamma? It's a relativistic term. If a particle is moving with very high velocity, which approaches to the velocity of light, then this term comes in the picture. And what is the value of gamma? 1 over root of 1 minus v square over c square. And de Broglie wavelength lambda becomes Now the question comes in our mind that how fast the de Broglie wave travel. Since we associated a de Broglie wave with a moving body, and what we expect that the wave has the same velocity as that of the particle or the body. And let we see if this is true or not. Now de Broglie wave velocity, and sometimes we call it phase velocity also. Velocity is nu lambda, nu is frequency, and lambda is the wavelength. So this lambda is de Broglie wavelength, and we already know the relation. Lambda is equals to h upon gamma mv. Now the quantum expressions we know well. For energy, it is h nu as well as gamma mc square, relativistic energy. Both are equal, both are E. So equating the two and finding nu from here. Now substituting lambda and nu in the above relation of the phase velocity, and phase velocity becomes equals to c square over v. Now because v is always less than c, v is always less than c, what it implies? Phase velocity becomes greater than the velocity of light. Is it true? The question comes in mind. The phase or the wave velocity of the de Broglie wave is greater than the velocity of light. So there's a problem. So we are discussing the waves of probability. Now in case of the water waves, the quantity that varies periodically is the height of the water surface. On the other hand, in case of the sound waves, it is the pressure which varies. And in case of the light waves, electric and magnetic field varies. Now then what is that varies in the case of the matter waves? That's the question. And well, the material particle like electron can have the wavelength, and the de Broglie showed that the wavelength is lambda is equals to h upon the momentum. H upon p, where p is the momentum. Then what exactly is waving? This is a typical question. And conceptually, it is a little strange, because in water waves, it is a bunch of water that is oscillating up and down. In case of string waves, the string is moving up and down and extend to the space. And in case of the electron wave, then what is the wave itself? That's the question. Think of it and write me in the comments box. What is whirring in case of the matter waves? How it is solved now? We are coming to the group velocity. And how we find the group velocity? Let us consider that we consider a wave group. Or sometimes it is called wave packet. And it arises from the combination of the many waves. And let me consider two here. And of the same amplitude, but slightly different frequencies and the wave numbers. Slightly different angular velocity d omega. D omega is the change in the angular velocity, and similarly there is a change in the wave number, which is dk. So the two waves, they differ with d omega and dk. So first of all, I'm writing y1 and y2. So you know there are two waves, y1 and y2. This is omega, but this wave differ. It is omega plus d omega. And second wave differ by with wave number also. Here the wave number is k, but here it is k plus dk. Okay, and let me apply the principle of superposition. So therefore the resultant wave becomes y1 plus y2. So adding up the two. Now here there is a trigonometrical relation, cos A plus cos B. So cos A plus cos B is cos alpha plus cos beta is 2 cos alpha plus beta by 2 cos alpha minus beta by 2. And we know very well what is alpha here and what is beta here. Substituting the values of alpha and beta here, which is, you know, this one is the alpha and this whole is the beta. Substituting these values in this relation and a very simple calculations, and you will get the y. So this is the expression of y. So please do yourself the calculations. Now because here this is, you know, d omega, it is in addition with 2 omega, because d omega is small and may be neglected in comparison with 2 omega. dk is neglected in comparison with 2k. Now here d omega is not neglected because there is no comparison of it. And here dk is not neglected because there is no comparison here. In comparison they are neglected. Okay. So the equation becomes, now this is a very interesting equation. You know why it is interesting? Because this is the same part like a wave. Okay, like this wave y1 of angular frequency omega and wave number k. But this additional part here, there's a you know, another wave of angular frequency d omega by 2 and wave number dk by 2. Now this is superimposed upon the wave. This is the important part. Like it is a modulation. This is the modulated part. Okay, changed, and you know, this is a new one, you can see, and very interesting information is contained in this part. So this is the original wave. This is, you know, this is superimposed part. So this is actually an envelope in which the two waves contains, and it is called a wave packet. Right? So this effect is called modulation. That is to produce a wave. We have produced a wave group. Now phase velocity of the individual wave is, you know, nu lambda, right? And nu lambda can be written like this, no problem. 2 pi and 2 pi, no effect. And lambda is written here, you know, 2 pi over lambda. And it comes in denominator and becomes the same term, nu lambda. But you know, 2 pi nu is what? It is omega. 2 pi over lambda is what? It is wave number k. So phase velocity of the individual wave is omega over k. So here the phase velocity is there, which is omega over k. Now in the group velocity, the group velocity The group velocity is what? D omega over dk. D omega over dk is the dispersion relation and may be written as d omega over dv and dk over dv. Okay, there's no effect in this equation because dv is here and dv is here. So let me write it here. Now omega is 2 pi nu and h nu equals to mc square. We find nu and substituting here. Okay, that is 2 pi mc square over the root of this. This is omega, right? Writing in the numerator. So differentiating with respect to velocity, you differentiate yourself. I'm just writing the result. Very simple differentiation. Now k is 2 pi by lambda and lambda from the de Broglie relation, gamma mv. Okay, and again factor it in numerator, and now differentiating this also with respect to velocity. You do the differentiation yourself. Now substituting the two values dk over dv and d omega over dv here, and the group velocity becomes simply equals to v. So very interesting. What is v? Velocity with which the particle was moving, and group velocity coming out to be the same as that the particle velocity. Okay, thank you. Well, the phase velocity of a wave is equals to angular frequency divided by the wave number, that is omega upon k. So in case of a single sine wave having a single frequency and a single wave number. Okay, this is the velocity of the component wave with a particular wave number k, that Vp is equals to W divided by k. Now secondly, the frequency depends on the wave number. Frequency depends on the wave number. So that is, the waves with different wave numbers then may travel at the different phase velocities. So therefore the waves becomes increasingly dispersed as the time goes forward. Hence the group velocity, when we derive that d omega over dk, the name is given dispersion relation. The group velocity is d omega divided by dk. So it is a bit like race cars traveling down a race track. Some cars travel faster or slower than the others, and individual cars traveling at the different speeds will become increasingly separated with the passage of the time. So that is there. Okay, that is what the case is. The wave becomes increasingly dispersed as the time goes forward. Now again keep in mind, the phase velocity corresponds to the velocity of each individual wave component, whereas the group velocity is the velocity of the entire waveform altogether. And you can also think of it as the average velocity of all the component waves. And let's going back to our race car analogy. The group velocity is like the average velocity of the race cars. Although the individual cars are traveling at the different speeds. So all the cars usually travel at a similar speed and therefore end up traveling more or less in a pack. So the group velocity is like the velocity of the whole pack of cars.